So now that you know about functions of several variables, we will go on to theme 1.2, which is on partial derivatives. You will find the theory section of this in your calculus textbook, section 14.3, page 911 to 920. So let's start with the definition of a partial derivative. So the basic definition of a partial derivative is almost like a slope. So usually if you just had y is equal to x, you would say that the slope is fx plus h minus fx over h as h goes to 0. But in this case, when you derive a multivariable function towards one of its variables, let's say you have f of xy, and you want to derive it towards x. So you change the x, but you keep the y constant. So the y is seen as a constant, and then you minus the original point over the change in x. So graphically depicted, it would look as follows. So you have your surface, which has this formula, and then you keep the y constant, you choose a y, and you want to see what the partial derivative is at the point. So in here would be 1 and 1, because you want to see what the partial derivative is at x is equal to 1 and y is equal to 1. So then you'd add an h. So let's say you can add an h of 0.1, and then it would give you a different function value that you can use then over the change, which was 0.1. But as the h's grow smaller, obviously they will never become 0, but as they go very, very small, it becomes just a derivative towards x. So how this works is you take your function and you look at all of the terms that have an x in them, and you derive that term. But looking at y, you would look at it as if it is a constant. So this would become 0, and this would also become 0 when you derive it. So the partial derivative of fxy towards x would become negative 2x. And then the same goes for a partial derivative of fxy towards y. You keep x constant, and you change your y. So then your partial derivative of fxy towards y would become negative 4y, because x squared would then become a constant, as 8 is, and the only term with a y in it is negative 2y squared, which if you derive it becomes negative 4y. And this is what a graphical depiction of the derivative towards y would look like. If you want the partial derivative of fxy towards y at point 1, 1, then you keep x constant, you go onto the curve, and you choose a point which is h away from the point that you are investigating, and then you say that point minus this point divided by the distance between them. So that's just the basic definition, but usually you would just derive towards your y. This is just the basic definition, but you can be asked to apply it when you're giving tables with values, as you can find some of the examples that are given in your textbook. An example would be a function of x and y is equal to x cubed plus x squared y to the power of 4 minus 2y cubed. So let's say we want the derivation of fx towards x, and that would be equal to 3x squared plus 2xy to the power of 4. Because if we look at the terms that contain an x, it is the first one and the second one. And since if we take the partial derivative towards an x, we take y as a constant, this whole term would become a constant. So when we derive towards x, this would just become 0. And the same is for the partial derivative of fxy towards y. So you look at the terms with a y in it, and then you derive them, and if it doesn't have a y in it, as x cubed, you see it as a constant and it becomes 0. So this would then be your derivative towards y. Now let's look at implicit differentiation. it's all nice when you have your dependent variable on one side and your independent variables on the other. But let's say you want to partially derive towards one of your independent variables, but you can't seem to get your dependent variable on one side. Then you would have to do implicit differentiation. So for an example, let's say we have x cubed plus y cubed plus 2z cubed plus 8xyz is equal to 1. So it is pretty clear to see with the orders of z, it is not going to be possible to get z on one side and x and y on the other side. So then we apply implicit differentiation. So if we want the partial differentiation of z towards x and or z towards y, this is what you do. So if you want it towards x, we keep y constant. If you want it towards y, you keep x constant. So in the case where we want the partial derivative of z towards x, this is what we'd follow. So you derive every term with x. You would derive, and then let's say you encounter a z term, you would derive that as well, but you'd have to remember to multiply it by dz dx. And the same for this term that has 8xyz. Now remember, when we get dz dx, we are deriving both x and z. But when you derive z, you just multiply this term. So this would become a product rule. So you have 8yz plus 8xy dz dx is equal to 0. And then what you can do is you can just take out these terms and simplify it. So then you would have dz dx times 6z squared plus 8xy is equal to negative 3x squared minus 8yz. And then further simplified, this would be your partial derivative of z towards x. And you would do the same if you have to get dz dy. You would keep x constant and derive towards z and y. But when you derive towards z, you just multiply a dz dy term to it. As follows. So let's say you want to derive towards y for z. So then you would have 3y squared plus 6z squared dz dy. Since we derived z, we have to multiply by dz dy plus 8xz, this is following the product rule, plus 8xy dz dy is equal to 0. We then take out this term and you will find the following. Then you simplify it and that would be your partial derivative of z towards y. And that is the simplified implicit differentiation. So now we can talk about higher order derivatives. So let's say you want to get the partial differentiation of x, but you are deriving the first order partial derivative of f towards x. So let's say you want to have d dx, but of df dx. So that would be your second order derivative. Now this can become a lot more complicated. We usually call this f of xx and f of xy because you first derive towards x and then you derive towards y, and here you derive towards x and then to x again. So it's basically just an iterative process where you first derive to the one variable and then you can derive to the other variable again or to a different variable. So this would be your combination if you only had two variables and you're only going to a second order derivative. For example, let's say your function is f of xy is equal to x cubed plus x squared y cubed minus 2y squared. So they're asking you to get f of x and f of xy and f of yy and f of yx. Right. So first you would get your first order derivative. So you would derive f towards x, which is 3x squared plus 2xy cubed. And then you would derive f towards y, which is equal to 3y squared x squared minus 4y. Then you can derive f of x towards x again, which will give you 6x plus 2y cubed, and then you derive f of y to y again, which would give you 6yx squared minus 4. Then you can derive f of x towards y, which will give you 6xy squared, and then you can derive f of y towards x, which will give you 6xy squared. And if f of xy and f of yx are both continuous on the domain of fxy, then f of xy at a point is equal to f of yx at a point. And this, you'll see, is called Clairaut's theorem. So basically, Clairaut's theorem is just telling you that f of xy is the same as f of yx if they are both continuous on the domain of fxy. So let's do some study guide problems. So for the study guide problems, I would like you to go to exercises 14.3 in the textbook. So question 10, you'll see a contour map in the textbook, and it would be favorable if you could look at the contour map. So in this question, they ask you to estimate the partial derivative of f towards x at point 2, 1, and the partial derivative of f towards y at 2, 1. So we know from definition of the partial derivative of x at a point that f of x at a point is approximately f of 2 plus h, 1, minus f of 2, 1 over h. So this h is something that you'll have to choose on your own by looking at the contour map. So basically how you choose this is the levels that you see on the contour map is basically your function values. So you'd have to check where you can get another function value. Let's say it's 10 and the other one is 15. And let's say that you have at 2, this is your x and your y. So at 2 you have a function value of 15, right? And let's say at 3 you have a function value of 10. So then you can make your h1 so that you can have the function value at 3. And then you just have this as 1. Right. So in this case, in the contour map, h you could choose as 1. So then you have f of 3, 1, remembering that the y stays constant, minus f of 2, 1 over 1. And reading it off, this is just values that I chose now, but on the contour map, you'll see that the function value at x is equal to 3 and y is equal to 1 is 14, and the function value of f at x is equal to 2 and y is equal to 1 is 10. So then you'd have a partial derivative, an estimated partial derivative of x as 4, which is a positive slope. So you can see that as it moves along x, not in this case, but as it moves along x on this contour map, that it is going upwards. So the same can be done for your partial derivative towards y. You look at the function values that you can find. So here you have 15, let's say here you have 9, and then you can choose a value for yourself, and here you have some arbitrary number, let's say it's 8. Then you choose that value, let's say this is 4 and this is 1, so then h should be 3. Obviously you'd want to choose the smallest h you can possibly get, but be accurate within the bounds of the information that they give you on the contour map. So in this case, there was a function value at x is equal to 2 and 2 and x is equal to 2 and 1. So h was also 1. And then the function value at 2, 2 was 8, and at 2, 1 it was 10. So then you have a negative slope, which means that as it goes into the y direction, the slope decreases. So you are going downwards as the slope as you go along y. Next, they ask us to find the partial derivatives of the following function. So the function that we've been given is z is equal to 2x cos xy. So to get a partial derivative, we need to get it towards x and y. So if we want the partial derivative towards x, we take y as a constant. But we can see here that we have an x and we have a cos x multiplied by a constant. So we'd have to utilize a product rule here. So doing that, first deriving towards the x, you have 2 cos xy, and then deriving towards cos part, you have plus 2x times negative sine xy, and then taking the chain rule inside here, you would have a y. So that would be the partial derivative of z towards x. Now if we take it towards y, we then just assume that x is a constant here and here. So we do not have a product rule as with the partial derivative towards x, but we only have this y inside the cos. So you only derive the cos towards the y. So here you would have negative 2x times sine xy times x, which then becomes negative 2x squared sine xy. So that would then be your partial derivative of that function. The following function is u is equal to 2x to the power of y over z. So this is where you have to really just do it slowly and make sure you understand what you are doing. Right. So let's say you want the partial derivative of u towards x, right? So we can see that x here is towards x is to the exponent of constants, because if we are partially deriving towards x, we say y and z are constants. Okay, so it would be like you're saying x squared, like 2x squared, for instance. So if we have x to the power of a constant, we know that we multiply out the constant and then we say the constant minus 1. So that is just a basic rule. It might look confusing, but if you just keep your head together, you will figure it out. So the partial derivative towards y is a bit more complicated, because now, if it makes it easier for you to imagine it, instead of having x and z, you can just write it as, let's say for instance, 2 times 3.5 y. Okay, so let's say you have a constant to the power of a half y. Okay, so derivations with constants to the power of variables usually cause us to have a ln of the constant times the derivation of the variable up here. So we would have 2 ln x times x y over z, because this stays constant but it gets multiplied by the ln of the constant value, times the derivation of y over z. So y over z, if it's derived, so if you have half y, if you derive a half of y, you just have a half left, so you'd have 1 over z. So if it makes it easier for you to actually do the derivation and less complicated in your mind, you can just make the x and the z values so that it could look better. And then the partial derivative towards z, you would do almost the same as here, except this would be different, because if you have 1 over z, then it becomes negative y over z squared. So yeah, that is just how you would do the partial derivatives of those functions. Now the last question is, verify that Clairaut's theorem holds with the following function. So you have f of xy is equal to ln of x plus 3y. So we know that Clairaut's theorem says that f of xy has to be equal to f of yx if they are continuous in the domain of f of xy. So the domain of f of xy, since we have a ln, we know that x plus 3y has to be greater than 0. So x has to be greater than -3y. So that's just the domain of the function. So now we can take the partial derivatives towards x and y, which should be pretty easy because you are just saying for the partial derivative towards x, you're saying y is constant, and the partial derivative towards y, you're saying x is constant. So this would be the partial derivatives that you would find. And then you would get the partial derivative of f of x towards y, which should give you -3 over x plus 3y squared, and the partial derivative of fy towards x, which would give you exactly the same. And now we see that f of xy is equal to f of yx. Therefore, we have verified that Clairaut's theorem holds. And that is the end of the study guide problems.